Hello, everyone, and welcome. Have you ever spent hours, maybe even days, crafting what you thought was the perfect prompt for an AI? The art of asking a large language model a question just so has become a celebrated skill, but I'm sure you've run into this frustrating scenario where 5 messages into a conversation, the chatbot completely forgets the most important instruction you gave it, or an AI coding assistant which was a genius just a moment ago, starts suggesting code that completely ignores your project's entire architecture. Let me be clear, this is not a failure of the prompt, it is a failure of context. For the last couple of years, the AI community has been in the era of prompt engineering. Some have even called it vibe coding, just tweaking words until the output feels right. But that honeymoon phase is over. To build anything real, anything that scales and is reliable, we need to shift from crafting sentences to architecting systems. This marks the beginning of the era of context engineering. The most important question is AI is no longer what should be asked of the model, it is now what does the model know when it is asked. Context engineering is the discipline of designing and managing the entire system's information ecosystem that surrounds an AI model. It's about making sure that the model has the right knowledge, memory, and tools to do its job accurately and autonomously every single time. A helpful analogy is to think of staging a theater production. Prompt engineering is like giving a brilliant idea to a talented actor, but context engineering is everything else: the stage design, the lighting, the props, the script cues, and the other actor lines. Without the right stage, even the best actor would deliver an ineffective performance. Context engineering sets the stage for the AI to succeed. The distinction here is fundamental. Prompt engineering focuses on a specific moment in time, while context engineering governs the entire life cycle. Let's break that down. Prompt engineering is about a single input output pair, the immediate instruction. Context engineering, on the other hand, manages the entire information ecosystem from memory, tools, history across different sessions. The goal of prompt engineering is to get one high quality response for one task. The goal of context engineering, on the other hand, is to build reliable, consistent, and scalable AI systems that perform well over time. So, while prompt engineering is an art of wordsmithing, context engineering is a discipline of system design and software architecture. It is the difference between writing a brilliant function call and architecting the full service contract with all its dependencies and state management. So, to engineer context, we first have to understand where it lives, and the place is called the context window. The most effective way to think of the context window is as the AI's short term memory, or its RAM. It's the finite space measured in tokens, which is roughly analogous to words, that holds everything the model can see at one time. When you send a prompt, you're not just sending your question, you're sending a whole bundle of information that fills up the RAM. And that bundle, the complete context, is made up of several components that systematically assemble. First, you have system instructions. These are high level rules that define the AI's persona and its constraints. Then there's a direct user input, the conversation history for short term memory, any retrieved knowledge from external documents, which is the basis for RAG, or Retrieval-Augmented Generation. And finally, tool definition that describes any APIs the AI can use. Now, a common assumption is that with these new massive context windows, some over 1 million tokens, you can just stuff everything in there. But there's one of the biggest, most costly misconception in AI development today. More context is not always better. In fact, it can be substantially worse. Recent studies have identified a phenomenon called context ROT, the progressive decay in LLM's performance as the context gets longer. The model just doesn't process the 100,000th token with the same fidelity as it did for the 100th token. Its attention gets diluted, its reasoning gets muddled, and its performance become unreliable. This happens for a few key reasons. First, there is a context distraction where irrelevant information in the prompt overwhelms the model's original instruction. Then, you have context confusion. Too many details, especially conflicting ones, can confuse the model. For instance, giving an agent too many tools definition can lead it to choose the wrong one or fail to choose anyone
anyone
at
at
all.
all.
Then
Then
there's
there's
also
also
context
context
poisoning.
poisoning.
A single piece of bad data, like hallucination from a previous turn, can enter the context and poison all subsequent responses that reference it, leading to a cascade of errors. And finally, there's the lost in the middle problem. Studies show that models pay more attention to information at the very beginning and at the very end of the context, often forgetting crucial details buried in the middle. This
This
reveals a
reveals a
central
central
engineering
engineering
challenge. There's an inherent tension between giving the AI a rich, complete view of the world and the necessities of avoiding performance degradation, high costs, and increased latency caused by excessive information. The goal
So how do we
isn't
solve
just
these
to add
problems?
context, but to optimize. The industry is converging onto four key strategies. I like to think of them as the four pillars of context engineering: write, select, compress, and isolate. Mastering these is the key to building robust and intelligent AI. Let's start with the first pillar, right? The most straightforward way to manage a limited RAM is to use a hard drive. The right pillar is about strategically saving information outside of the intermediate context window for later use. This can be done with scratchpads for short term memory, where an agent jots down its plan or intermediate results for a single task. This keeps the main context window clean and focused. It can also be done with memories for long term storage, allowing an agent to return information across different sessions. This is how you build an AI that learns about its users over time, storing preferences in a system like a vector database. Once the information is written externally, you need to find a way to get it back at the right time. This brings us to the second most and arguably foundational pillar: select. This is the art of pulling only the most relevant pieces of information into the context window for a specific task at hand. The core technique for selection is RAG, or Retrieval Augmented Generation. RAG connects an LLM to external knowledge bases like your company's internal document or a product manual. Instead of relying on its static training data, the LLM can look up fresh, relevant facts on the fly. It's crucial to understand that RAG is not the same as context engineering. RAG is the primary technique used to implement the principle of selection. Context engineering is the overarching discipline that dictates when to use RAG, when to put in the RAG system, and how to combine it with other tools and agents. Now, our third pillar, selection, helps fight irrelevance, but even relevant information can be too long, consume tokens, and increase latency. This is where compress becomes essential. This pillar is about retaining the essential meaning of information while shedding as many tokens as possible. Techniques here include context summarization, where a smaller, faster LLM generates a concise summary of a long document or a chat history first. Another is using structured data components like compact JSON objects instead of long paragraph, which models are great at parsing. Finally, our fourth pillar is isolate. Sometimes the best way to prevent different pieces of context from interfering with each other is to keep them completely separate. This pillar is about splitting context into walled off compartments to improve the model's focus. One of the most powerful ways to do this with multi-agent system, where you decompose a complex problem and assign subtasks to a team of specialized agents. Each agent has its own separate context window, its own instruction, and its own tool. You can also isolate at the tool level. Instead of giving an agent 50 tools at once and confusing it, you can pre-select 3 to 5 most relevant tools for the current task and isolate the prompt to only include those definitions. This dramatically improves the agent's ability to choose and use the right tool. Theory is great, but let's make this practical. We're going to design a smart corporate assistant to help an employee, Sarah, to write her quarterly performance report. This will show how all four pillars work together. Let's see what this looks like in practice. I've got a GitHub repo pulled up here, and by the way, I've left the link for this down in the description so you can check it out. To help us break it down, I'm using the new browser extension from Perplexity. It's pretty cool. You can just open a tab and ask it to summarize or describe what's happening on the page. It's perfect for getting a quick handle on a project like this. So, Sarah's initial prompt is simple. She says, "Help me write my Q3 performance report." A naive system with no context engineering would pass this directly to an LLM and get back a generic, useless template. But a context engineered system is much smarter. First, we use the right pillar. It uses the right pillar. The system has been interacting with Sarah for weeks and has written her preferences to a long term memory store. It knows she's a senior product manager who prefers a concise tone. Next, it uses the select pillar. The system employs RAG to select relevant information from the company base. It receives two critical documents: the official sales performance PDF and Sarah's own project notes from the page title. But these documents are long. Putting all the raw text into the prompt would be inefficient. So system uses compressed pillar, a summarization model that processes both document and extracts key bullet points, which is far more token efficient. Finally, the system uses the isolate pillar. It provides the agent with a tool to get feedback from Sarah's direct reports, but to prevent confusion, it isolates the prompt to include the schemas for only the specific tool, not the other 50 tool that the agent could potentially use. Now, all these pieces are assembled into a final context rich prompt that the LLM will actually see. So, where do we go from here? We've gone from simple prompts to sophisticated multi component systems. The four pillars write, select, compress, and isolate are the architectural blueprint for building reliable, scalable, and truly intelligent AI. This isn't just a technical exercise, it's a strategic imperative in the enterprise world. The real competitive advantage isn't the specific LLM a company uses, but its proprietary data. Context engineering is the bridge that connects the power of modern LLMs to the unique value of internal knowledge. It's how you transform a generic chatbot into an expert colleague that understands how your company works. The field is already evolving towards workflow engineering, where developers design explicit multi step sequences of these techniques to solve even more complex tasks. We are, in effect, building the equivalent of an operating system for LLMs, where context is managed as a core resource, just like memory or CPU cycles would be. The era of simply prompting an AI and hoping for the best is over. The future belongs to those who can build the world around the AI. The new mandate is to treat context not as just a mere input, but as the most critical product to be designed, visioned, tested, and optimized relentlessly. Because in the age of AI, context is everything. And thank you so much for watching.